Hello students. So now we are going to discuss the solution of partial differential equation. That is, in particular we are going to discuss about the solution of non-homogeneous partial differential equation, and the method is direct integration. So we are going to find the non-homogeneous uh, partial differential equation solution by integrating directly. So now we know already what is a non-homogeneous partial differential equation. So here I consider one simple example. So this is the non-homogeneous PDE where x is the independent variable and u is the dependent variable, and we must know that it is understood that u is a function of x and y. Even though y is not there in the equation, it is understood that u is a function of x and y. So here we directly integrate with respect to x, as we have the derivative with respect to x. So we integrate with respect to x directly. So that result is given by u equal to, so integration of x square is given by, that is x cube divided by 3, here I wrote, and also the integration constant is given by k. So in this case, in this method, we are going to consider the integration constant as a arbitrary function of other variable. So here the other variable is a x, the other variable is a y. So therefore we consider the arbitrary constant as a arbitrary function of y. That is, the solution is given by u equal to x cube divided by 3 plus arbitrary function of y. So, so now we are going to consider some examples. So this is a one non-homogeneous PDE where u is the dependent variable, x and y are the independent variables. So once we confirm that it is a non-homogeneous partial differential equation, we find the solution by direct integration. So we have dou square u by dou x square. So first we integrate with respect to x. So integration of dou square u by dou x square is given by dou u by dou x, and then integration of x plus y. And in one thing you remember, when we are integrating with respect to x, so treat y as a constant. So therefore the integration of x is given by x square by 2, and the integration of y, which is a constant, so that is given by x into y, plus we have to consider the arbitrary function of other variable. That is, when we are integrating with respect to x, we consider the arbitrary function of y, that is f of y we consider. So now again we integrate with respect to x. So integration of dou u by dou x is u, then integration of x square by 2 is x cube by 6, plus integration of x is given by x square by 2 and y constant. Then f of y is a constant here because we are integrating with respect to x, so we treat this f of y as a constant. So therefore keeping constant and integration of 1 is given by x, plus now we consider the arbitrary function of y again. So we are integrating one more time, so we consider the one more arbitrary function of y, that is g of y. So this is the solution of the given non-homogeneous PDE. Okay, so this is also one similar example. Now we are going to consider one different example where some conditions are given. So this is the example, and this is the non-homogeneous PDE where x and t are the independent variables, u is the dependent variable. Now some conditions are given. First, as usual, we find the solution. So later I explain for what the conditions are given. So here the given equation is dou square u by dou x dou t equal to e raised to minus t into cos t. So now we integrate first with respect to x. Actually we can integrate either with respect to x or with respect to t, but we are going to integrate with respect to x only, with respect to x only, because when we integrate with respect to x, we remain with dou u by dou t. This dou u by dou t we are using in the next step because the value of dou u by dou t is given, so this value we are going to use here. That's why we have to integrate first with respect to x, not with respect to t. So therefore we, after integrating with respect to x, we get dou u by dou t, then e raised to minus t which is a constant, then integration of cos x is sin x plus, so here the arbitrary function of other variable means when we are integrating with respect to x, we take the arbitrary function of t, so that is f of t. So now integrating again with respect to t, then u equal to integration of e raised to minus t is minus e raised to minus t, and sin x is a constant, plus now we are integrating with respect to t means we consider this f of t as a function, not a constant, because with respect to t we are integrating, so that we integration of this small f of t we write as a capital F of t. So this is the notation we are using, plus arbitrary function of other variable, that is we take the for arbitrary function of x. So we got the solution of the given partial differential equations. Now this solution containing the arbitrary functions of t and the arbitrary function of x. Now we are by using the given conditions, we are going to find the values of the arbitrary functions. The one condition is, so here the one condition is u equal to 0, then t equal to 0. This is the one condition given, and the second condition is dou u by dou t equal to 0 and x equal to 0. This is the second condition. So first we use the condition dou u by dou t equal to 0 and x equal to 0 in equation 1, putting dou u by dou t equal to 0 here, and then x equal to 0. We get from equation 1 0 here equal to x is 0, sin 0 is 0, so this term becomes 0, then equal to f of t. So therefore the value of f of t is 0. So therefore the capital F of t is also 0. So therefore by substituting f of t value 0 in the equation 2, then we use the second condition. The second condition is u equal to 0 and t equal to 0. Putting u and 0 and t 0 here, u is 0, e raised to 0 is 1 into minus sin x plus g of x. Therefore the value of g of x is sin x. So now we got the values of the arbitrary functions. By substituting the values of capital F of t as 0 and g of x equal to sin x, we get the particular solution as u equal to minus e raised to minus t sin x plus, this is the f of t is 0 here and g of x is sin x. So this is the solution, and some additional question is given, that is when the value of t is infinity, the value of u equal to sin x. Means in this obtained solution we are going to put the value of t as a infinity, then we are going to get u equal to sin x, that is e raised to minus infinity is 0, because e raised to minus infinity is 1 by e raised to 1 divided by e raised to infinity we get, that is 1 by infinity, so 1 by infinity is 0, so this term becomes 0, therefore we get u equal to sin x. So this is the one example on the solution of non-homogeneous PDE by direct integration.